We ended talking about solubility. We ended talking about what is an electrolyte. Keep in mind, an electrolyte is nothing more than a salt, right? A salt that we are going to put in water.
Is
Now,
this the
PowerPoints?
yeah.
It's up there.
Okay.
So the PowerPoints for chapter 2 are up there. When you look at these intermolecular forces, understand that the polarity of water, that means the partial charges in water, exerts an incredible force. It allows H2O molecule to react with another H2O, and another, and multiple H2O molecules. Right? When that happens, you have a lot of these attractive forces. Now, the hydrogen bonding isn't very strong. Each bond is pretty weak. It's easy to dissolve by itself. But because there's so many of them, it can start reacting, and you add it all up, and those hydrogen bonds are incredibly strong because of that additive effect. So it's kind of cool. And the best example of the strength of the hydrogen bond is that because of, do you see these partial charges? Remember that weird sign? This is actually the Greek symbol for delta. This delta sign is partial. Partial positive, partial negative. So when you see oxygen having a partial negative charge, it means that it's stronger. It wants to steal hydrogen's electrons so that it can keep it for itself. It's more electronegative. Hydrogen, being slightly weaker, has some of its electrons kind of taken for it. So it's got a partial positive charge. Remember, when you gain an electron, electrons are negatively charged. So when you gain an electron, you become negative. When you lose an electron, you become positive, the exact opposite. Now, it's not a full negative charge because they're still sharing, it's still a covalent bond. If it was a full charge, that means oxygen would have stolen that electron immediately. Now, water, because it's got these partial charges, can separate sodium chloride and even potassium chloride. So all these positives and negatives start to attract each other. Sodium has a positive charge, so what happens? All the negative charge, or partial negative charges in water, surround sodium. Chlorine, or chloride now, has a negative charge because sodium chloride, when you put them together, right, sodium has one extra electron, chloride wants that extra electron. So sodium passes that electron directly to chlorine. When that happens, it gives a negative charge because it gains sodium's electron. Sodium's electron on chlorine makes it a noble gas, right? It's got enough electrons to be noble gas-like. And it's got a negative charge, so the partial positive charges found on the hydrogens of water that we see in blue here, those partial positive charges surround the negative charged chlorine. Now you have water molecules surrounding sodium, water molecules surrounding chlorine. They can't combine anymore. The crystals then start to separate. Now, what happens if the water evaporates? The water evaporates, well, there's no more separation. Sodium and chloride can interact again. So they can form crystals if water is removed, like by evaporation. We use the example of a saltwater fish tank. Right? When we have a lot of water in a saltwater fish tank, you don't see the salt crystals. Why? Because you have a lot of water separating sodium from chlorine. Right? So when that happens, it gets dissolved. But what happens if you don't do anything to it? Just let it evaporate over the course of many, many months. Well, the water evaporates out. Now you can't have the water molecules separating sodium and chlorine. Because you no longer have it separated, well, the sodium and chlorine start to react again. And you start seeing more and more crystals being reformed. Right? So in terms of electrolyte, basically a salt when we have it with water and mix it together. Now the cool thing about electrolytes is this. Electrolytes have the capacity to conduct current. So I'm going to highlight this because it's so important. if I can. Right? So I would highlight it, and for some reason not letting me, and I would write this part down. Right? Electrolytes have the capacity to conduct an electrical charge. Remember, what is an electrolyte? Salt and water. Right? You have the sodium that's positive, the chlorine that's negative, all the partial charges in water. And what they do is that, well, there's a lot of charge, right, in salt water. So those electrolytes then, because of the partial charges and full charges, have the capacity to carry an electrical current. And again, think about what happens when you have a battery, right? Even the small AA, AAA batteries that we have, right? They use the same basis. They don't use something quite like salt water because salt water is very liquidy, right? It will just spill out. They use sodium with stronger water, or stronger acids, right? Sulfuric acid, some kind of acid is in there. It doesn't have to be something really, really super strong. In the car battery, it is something really strong. Now, in a car battery, have you guys ever had an old car battery and you need to jump your car and you notice like on those metal electrodes coming out where you put the wires on, notice that the older battery, the more white gunk is in there, right? Then you have to sometimes remove some of this white kind of solute that's surrounding the electrode. Why is there that white solute? It's because if you have sodium and you even have something like hydrochloric acid, right? When you have both of them, you have a charge that's occurring here. The hydrochloric acid takes the place of water, right? Water only has a partial charge. Hydrochloric acid will have full charges. And what happens when you have sodium and hydrochloric acid? You're going to produce sodium chloride as one of your solutes. That's the white gunk that we see. It's some kind of salt crystal. Now, obviously I won't go around and taste it to make sure it's sodium chloride, but it is some kind of salt that we see on the edges of all batteries. So even if you have a battery and you're remote, and you find it after you throw out your VCR or something, right? And what happens, you look at the battery. I don't know how you look at the battery if you don't have a VCR, but if you do, you see sometimes there's like this white gunk that's even in the battery. Now, the small batteries, like the AA, AAAs, they're not quite, they don't have like the same acidity as we see in like the car batteries. Car batteries need to be stronger. They need to give you a much stronger spark. So you need much stronger acids. Non-electrolytes, solutions made by molecules that dissolve in water but does not break apart. So salt water is soluble. It breaks the crystals apart. You separate sodium and chlorine, right? That is what we call formation of electrolytes. Non-electrolyte formation is, think about if you put table sugar and water, right? With table sugar and water, you can mix it up, but you'll always see some kind of film, right? It looks kind of blurry when you're looking at it. The reason is you don't separate the bonds in glucose and in sucrose when you mix it with water, right? That's a big difference. When we're talking about sodium chloride, we're separating it. So then the sodium and chlorine can't interact. When we're talking about sucrose, table sugar, well, you don't break apart the bonds, right? So you don't form electrolytes. Okay. So let's take a look at these reactions. What kind of reactions do we see? Number one, synthesis reactions, and then decomposition reactions. These are general name of the reactions we see in our body. And we do have a lot of these reactions occurring in our body, right? You guys have all heard of anabolic steroids. Most of us kind of understand when you're taking anabolic steroids, you get bigger and stronger as a result. That's why people take it. Human growth hormone does the same thing. What they do then is they increase the amount of anabolism that we see in the body. anabolism forms larger molecules. So anabolism is building up. Think of anabolic steroids. These are the class of reactions where we produce something much bigger from smaller molecules. Right? You have one molecule of amino acid. That by itself isn't very important. Right? You add another one. Then you add another molecule of amino acid. Pretty soon you get a long chain that becomes something that's useful. A protein, a hormone. Remember, proteins are made from amino acids. And that's what we see here. Here's our amino acid. It's got a very general shape right here. Right? You got, and by the way, we call it an amino acid because of this shape. All amino acids has an amine group, which is a nitrogen group. It's got a central carbon and then an acid group. Here's the acid group right here. Acid group, amine group. When you add it together, amino acid. Now, there are 20 different amino acids. The big difference between the 20 is what is found sticking out of this carbon, right? That central carbon has a functional group that you can switch back and forth. So it's a molecule that we can switch back and forth. Now, the simplest type of amino acid only has hydrogen in it, right? That amino acid is called glycine. Some of you might have heard of it before, right? Some of you might have heard of lysine. Lysine has this group sticking out of it, right? So the 20 types of amino acids, they all look slightly different when comparing this side chain, this R group. And you've ever watched, Jurassic Park, right? They try to limit the certain amino acids that you need to have through diet, and that was their way of having population control over the dinosaurs, was that they, make sure that those dinosaurs only get lysine from whatever the kind of food products that the lab made. Right? So if they try to get it in nature or throughout the rest of the park, they don't get enough of that lysine, which is what we call an essential amino acid. An essential amino acid you have to get through diet. You can't produce it by the body. Now, anabolic reactions build. We build bonds right here. As we build bonds, we're going to make something larger from something smaller. Now, in order to build a bond, we're going to remove water. And water here, down here. Now, some of you guys might have had chemistry a while ago. In chemistry, we're going to have reactants on one side. That's what we put in. That's the 2 amino acids. On the other side, here's an arrow pointing to the right, you're going to have the product, what you form by it, right? By adding those two together. When you put those 2 amino acids together, you start the process of building a protein. Now again, if this sounds kind of, foreign to you, you need to read chapter 2, right? And the only other good news is we kind of mention it later on, but we don't really talk about the whole chemical aspect of it directly from that point on. Anabolism allows us to produce large macromolecules that allows us to have the characteristics of life. We can form large carbohydrates. We can form glycogen from these synthesis anabolic reactions. We form proteins from these, right? We can form fats and even DNA and RNA from these type of reactions. Now keep in mind, what we're doing here is forming a different bond. By removing water, we form a bond now between amino acid number 1 to amino acid number 2. Here's that bond. Right, the more of these bonds, the larger the protein gets, the more functional it becomes. On the one end, you have anabolic reactions that builds up. On the other end, you'll have catabolic reactions that breaks down. So catabolic reactions are going to break down larger molecules. One builds, one breaks apart. So catabolic reactions, especially in our body, are usually seen when we are either fasting or after a couple of days, fasting becomes kind of starvation. Now, we'll talk more about the kind of reactions our body makes when we start to fast, right? Now, Muslims observe Ramadan, and from sunrise to sunset, they don't eat, they don't drink, right? How are people supposed to cope with that decreased amount of food intake? Well, actually, our body does a pretty good job. There's a reason why before sunrise, during the month of Ramadan, really early, most families come together and have a big meal. And then at sunset, they have a big meal afterwards to break the fast. There are reasons why we do these things. So we'll talk about those later on. It's kind of cool. What we're doing with these breakdown reactions is breaking apart larger molecules so then we can use the smaller ones, right? So we can make use of it. Example is this. When we are eating, there's lots of food, we are going to make lots of fat. There's almost no limit to how much fat we can store in our body. If you guys have seen My 600-Pound Life, yeah, you can see that there's almost no limit, right? And what happens then is when you build that fat, the more time you can kind of last when you are fasting and starving. Right? Now you try to tell somebody that's 600 pounds that they can't eat for a day, good luck, but if they have to, they can last like many months. Usually with the breakdown of the bonds, energy is released. Now the big take home I want you guys to know is this. I'm going to show you what glucose molecules look like. Glucose looks like this. Right? Sorry. And what glucose has, I know, you don't need to know it right yet. Glucose has a lot of carbons, 6 carbons. It's got a lot of hydrogens, 12. And it's got also 1, 2, 3, 4, 5, 6 oxygens. There's a chemical formula, all right? Glucose by itself, you know what happens to all these elements? Because you think the elements are important, right? Our body uses glucose as a fuel source to make lots of energy. So these elements that help make up glucose should be important. What does it become when we use glucose as a fuel source? It becomes carbon dioxide and water. Carbon dioxide and water. That's it. In other words, this is byproduct. This is waste our body produces in making ATP, our battery pack. Right? So what I'm saying is, it's not the elements and the atoms itself that's important. What's important in all of these chemicals is the reaction, the bonds here. These bonds, when we break it apart, those bonds, when we break it apart from each other, well, they release electrons. They release energy. All this other stuff becomes junk that we have to get rid of. All right, it becomes something that actually can kill us if it builds up. So, important concept is that it's not the actual elements in any molecule that allows us to survive. It is the bonds that connect those molecules together. And when we split apart the bonds like we see here, we can then make use of it. Now, some of you guys might have heard of lactose. Some of you guys might have heard of lactose and how it can make you feel if you eat too much of it, right? So what lactose is just a disaccharide, 2 sugar molecules together. The crazy thing is this, in our small intestines, we can only absorb sugars when they are separated. So when you have 2 glucose molecules are separated, we can absorb each one independently. We have a receptor for it. When they're attached, like we see here, we can't absorb anything. You need to break it apart first. And you can imagine, well, it's only one extra sugar, right? Well, what happens is that that extra sugar makes the molecule too large, and the receptor now cannot bind to it. Then it goes, you don't absorb it, it goes through your GI tract unabsorbed. That's not a good thing. So next thing that we'll talk about